Oh, so this is the traffic. This is just a way of writing half m omega squared x squared.
Yeah, but the numbers.
Oh, this paper, I don't know. You have to look up the paper. Yeah, I don't know what their numbers are. I mean, I know that the trap, you know, if I was to draw it on a scale, it would be something that looks kind of like this. It's not like the trap is really strongly shifting the energy between adjacent sites where the atoms are. That. But if you want to know exact numbers, just go look at this paper. There's a very exhaustive supplementary material part to this paper as well. Okay, so what are the types of measurements they do? All right, so one type of measurement they do is what I call a coherence measurement. So what they do when they do this measurement, and maybe what I'll do is talk a little bit more about this in case this doesn't make sense to you, is they have the atoms in there, they snap everything off, they're starting with a BEC, and they let the atoms expand at time of flight so they get a picture of the momentum distribution of the atoms. All right, so this is what the momentum distribution of the atoms looks like. All right, it's kind of a 1D system, and what you can see here is you can see the incommensurate lattices that are present. There are two wave vectors present, right? There's this kind of wave vector and this kind of wave vector of the atoms, okay? So that is what the atoms look like. You know, if you have a delocalized wave function across here with the two incommensurate periods present, that's what the momentum distribution of a superfluid in there looks like. Make sense? Okay. So what they do in this measurement is they turn up the disorder and they look at how the width of these features changes. Now, why is that interesting? So this is probably a weird measurement from your point of view. Let me talk a little bit more about it. Let me skip ahead to the slide and come back here. Okay, so what are they doing when they do this kind of measurement? Well, if you have a bunch of atoms, this is a way an AMO person thinks about this measurement and what that width of that central feature tells you. If you have a bunch of atoms and they're in this lattice, and here's a bunch of atoms with their van A orbitals here, and the phase of the wave function for all these atoms is the same, well, that's just another way of saying we have a delocalized state, and it's a Q equals 0, and it's delocalized across the lattice. And if I let the atoms, turn the lattice off and let those atoms expand into each other, then what I see is something here which has very small peaks that are well resolved that show you the k vector of the lattice, basically, which is built into the atoms, momentum function, right? One way to think about this is all these van A orbitals overlap, and then they interfere with each other, and this is just the interference pattern associated with something which has a periodic wave function. Okay, so that's one way to think about what's happening. Instead of having a case where I have a bunch of atoms now in these sites, and the phase has been randomized, okay? So the phase of the wave function of this van A orbital is different than this one, is different than this one. Now when I turn the lattice off and let these expand, what happens is that phase results in the kind of, that interference pattern getting kind of muddied up, and this is maybe not the best picture of that, but what will happen in that case is these features will tend to blur out, okay? And that's just because the interference is not as good anymore, right? You've got this random phase built into there, and the things are interfering, but the phases are varying somewhat. And eventually, if those phases vary completely from site to site, you just get a complete blur, where this is just the Fourier transform of the van A function for one site. And again, this is not the best picture, this is just schematic, okay? So that's why what they're looking at is the width of these central features as they vary the disorder, because they're trying to see something switch over from a situation like this to a situation like this, where the atoms are becoming localized at sites and kind of independent. All right, that's the hand-wavy picture. So that is what they're looking at here. So what they're looking at here is, and this is a typical, what people call coherence measurement in this field. So here's a bunch of measurements they do. Each one of these x's is a measurement. And here's a disorder divided by the tunneling matrix element, which they call J on this axis. Here's the interaction energy. Okay, so interaction energy, disorder. And in this case, disorder is controlled by the amount of that incommensurate lattice which is present. And here they're measuring the width of the central peak. So often in this direction, where the width is smaller, there's a longer coherence length. And where the width is bigger, there's a shorter coherence length. There's more phase fluctuations from site to site. And so the main observation here is not necessarily that there's any kind of localization, but just that the introduction of the disorder is certainly leading to increased phase fluctuations or a loss of coherence, right? So if I go and I look what happens at weak interactions when I crank up the disorder, coherence gets less, same over here. And there's some kind of phase diagram I'm trying to put on the top of this. All right, so that's what's called a coherence measurement. Nothing that exciting there, really. They also combined this measurement, and they pulled out 3 points here, red, blue, black. So 3 disorder strengths, so it's 3 disorder strengths here. And they did a transport measurement. So in the transport measurement, what happens is you have a trapped gas. Okay, this is not to scale, so the trapped gas spans many, many lattice sites. You apply an impulse and measure the resulting momentum. So it's kind of like in a solid, you apply a force, which is an electric field, which comes from a voltage, and you measure a current. That's kind of like what's happening here. All right, so they do this. You can do this in different ways. Of course, if you add a linearly increasing potential, which is just another word for a force, that just means the trap shifts, and the atoms gain some momentum, they measure that amount of momentum which is gained. So you should think about this as an analog of conductivity. Okay, so in this measurement, here's what's happening at these different disorder strengths. This is no disorder. The system kind of has a high conductivity, and that conductivity kind of falls away as they turn up the interaction strength here. Okay, and that's happening because in the clean system, it will cross over from being a superfluid to a mod insulator, but it's complicated because there's all kinds of inhomogeneous phases present. There's actually always kind of pieces of superfluid present. So the response here is very complicated. And as they turn up the disorder at low interactions, the sort of conductivity falls. And then as they turn up the interactions seem to foil the localization to some extent and restore some of the conductivity. Okay, so there's lots to say. They did many measurements that are in this paper, but sort of the observations are in this paper that yes, the disorder seems to reduce the conductivity. It's not clear here that localization has been observed in terms of an absence of conductivity. The interactions seem to fight the disorder and restore some of the conductivity. The disorder seems to destroy the coherence somewhat by introducing phase fluctuations between sites, which, you know, if that happens, that should reduce the conductivity, which is what you see here. Okay, so one other measurement they did, then I'll stop and ask for questions, is excitation measurement. And so this is an important measurement that's done in many AMO systems as well. So what's done here is you have the atoms in the lattice, and you modulate the lattice amplitude. So the laser beams that make the lattice, you actually just modulate at some frequency the laser power. Okay, so this modulates this amplitude. And what that does is that'll force atoms to tunnel to neighboring sites. Okay? And if another atom is there to tunnel to this site, the atom needs to gain energy U. So that means you should see something happen when you modulate that lattice at a frequency corresponding to U, because then you can do the work on the atom you need to do to force it to actually come over to the neighboring site and conserve energy. So here's some data where you can see this. This is with no disorder at high U. And so what you see here is that Mach gap. You see this is, okay, so this axis is the modulation frequency in units of J, or the tunneling. This is a measurement of how much energy has been deposited in the gas. This is more energy because the condensate fraction has been reduced going down on this axis like this. So this is U in these units. You can see there's a peak here right at U, where they've actually seen atoms transfer from site to site like this, from occupied to an occupied site, and generate a double occupancy. Right? There's a peak at 2U, and that just comes from the fact that there's also sites with 2 atoms present, and they're making those gain atoms. And this is what happens at very high disorder. That whole thing gets kind of smeared out. And this is a theory curve, I think by DeMarco on there, that includes Bose glass physics. And so the argument there is they're seeing the Bose glass emerge in pieces of this system, but there's a coexistence of many inhomogeneous things here. There's coexistence of Bose glass, superfluid, and probably a little bit of mod insulator. And so what's happening is very complicated. So there's no clear kind of like transition to an insulator, but there's some understanding of what's occurring. Okay, so that's an important lesson here, is that in many of these experiments, the fact that you're sampling a range of chemical potentials means that it's possible to have coexisting localized and non-localized phases, and sorting that out is a big challenge, actually. And that's kind of what you're seeing in these experiments here. That's why the conductivity never goes to 0. Okay, so that was complicated. So who has questions about these measurements and what was done here, how to think about them?
why do you modulate the amplitude? Why do you not modulate this one?
It's much easier to modulate the amplitude. And it does what you need. It's really just, technically, it's very easy compared to having the lattice shake back and forth. It's a way to sort of probe this excitation spectrum and look for what happens in the Mach gap, right? And what they're seeing here is the Mach gap is getting kind of washed away by the disorder. Yeah, good question. That's coming from, there are also, so there are domains of mod insulator here to start with. There's actually n equals 1 mod insulator, n equals 2 mod insulator in this experiment. So that's places where you have 2 atoms and a third one hops onto it. That's where that one comes from. Right, so an important lesson here is that many of these experiments in this trap, there are coexisting phases. And so to understand what happens, and as you add disorder what happens, often that has to be taken into account. And here that's under some control, yeah, theoretically. Yeah.
So how to think about this localization? Is it some zero temperature localization with some small interactions and starting the relative?
Well, okay. Yeah, I mean, yeah, so that's a good question, all right? And so I'm going to be kind of agnostic in this talk and not talk, I wanted to tell you what measurements were done and what was observed, and then, you know, the question of what is it is some other question, which is maybe complicated, all right? So I'm not going to comment a lot on this. You know, what most people think of this as is some kind of low energy experiment where they're looking kind of mostly at ground state properties, and that disordered Bose-Hubbard phase diagram I showed you, where this Bose glass creeps in. Of course, it's not at zero temperature, all right? It's definitely not at zero. None of these experiments are ever that close to zero temperature, right? And so there's definitely some effects of temperature here. And so what is this localization? You know, the traditional way of thinking about what's happening here is that phase diagram I showed. As you add disorder, these Bose glasses appearing, which are these kind of disconnected, spatially disconnected superfluid islands, which are compressible but are not conducting. But the complication of this experiment is that these are coexisting with other regions of the trap which are superfluid and probably also a little mod insulator as well. And so, you know, what I'll say is that generally, I'll come back to this, there's kind of a disconnect between, you know, somehow there's one thing that's happening here from low temperature to high temperature, however you want to think about it. There's some kind of localization with interactions which is occurring. And that's one thing which I don't think has been talked about a whole lot about, necessarily thought about, is how are these phenomena connected, okay? The big picture here too, from my point of view, is, you know, what you're looking at is you're looking at how are interactions changing Anderson localization. All right, so in 1D, they saw Anderson localization, things really well localized, great. But here, it seems like the interactions are actually fighting against the localization, right? And they have pretty clear evidence for this. And so that's an answer to this sort of question about what happens. And it's not surprising that the interactions should fight the localization. This is probably, you know, for bosons, you tend to think of what happens is there's kind of a screening effect where you start piling bosons on deep sites, and from the mean field interaction, it kind of smooths out the disorder which is there. So it's not surprising to see this, and people have thought about that for a long time. So that's kind of an answer to the question of what interactions do to Anderson localization. Well, for bosons, it seems like the interactions kind of fight against it, which is kind of what you're seeing in this plot of kind of, think about this as conductivity, kind of seeing, right, the disorder reduces the conductivity, and then somehow the interactions are restoring that. Yeah. So again, I'm taking a mostly agnostic point of view of what's going on here. I more want to just tell you in this part of the talk what's been observed, because the Anderson localization side of things is clear, right? And we understand Anderson localization, we have good hand-wavy pictures. Actually, what's happening here, we don't have a complete physics picture of how to think about this at all, actually. The interacting disorder problem is not a simple picture I can give you. Okay. So let me snap through a bunch of other things. Again, I'm just trying to give you an overview so that you can go learn more yourself. I mentioned this experiment yesterday. It's going to be hard to go through all parts of this. I may skip over this a little bit. But I mentioned that Schnabel's group looked at the difference between impurity disorder, where they had impurity atoms present, which through a mean field shift shifted the energies of the lattice around. They used this using a state-dependent lattice. And they looked at this and compared it against incommensurate lattices. And they looked at the difference between interacting bosons in these two systems. Okay. So now the impurity disorder, what it looks like is you have this kind of Bose-Hubbard model where there's an additional energy shift, random energy shift on every site that comes from the impurity atoms. And there's always a trap present. So they did a lot of measurements. To walk through all of this is complicated. What they tried to do was they tried to compare the incommensurate lattice case with the impurity model case, where somehow the size of the disorder, the amount of disorder was equal by some measure. Because they wanted to compare just, from an experimental point of view, how these things look different. So one thing they did was they did a measurement, an excitation measurement again, where they modulated the lattice, okay? And they looked at how much energy was deposited into the system. So this is a clean system at high interaction strength. And you see that Mott gap again, and it's in, there's more than one Mott insulator state present because there's an additional peak at 2U. And then they compared what happened is they added impurities and cranked up the amount of impurities there and added an incommensurate lattice. And these are somehow at equal measures of disorder. And you can see in both cases, this sort of nice Mott gap is kind of disrupted by the disorder and smeared out. Okay, so that's one measurement of what happens there. This is a really complicated plot, which maybe I should not go through, but tell you should go read this paper carefully, where they looked at a transport measurement and they looked at a coherence measurement, comparing the impurity case to the incommensurate lattice case. And again, trying to compare equal amounts of disorder to each thing. All right, and so they looked at, for example, with the impurities, they could see that this is kind of conductivity here. They could see more clearly in their experiment, localization happened. And the incommensurate lattice case. So with impurities, you're able to see, this is the clean case, the black data here. Okay, and they're seeing kind of localization curve because they go from a superfluid to a monoinsulator out here. And they're able to see that actually in their experiment with the impurities, as they increase the impurities, they're able to see actually the similar, so this is with some impurities, they're able to see that amount of lattice depth needed to get to a monoinsulator or some insulating state has gone down, okay? So that was kind of interesting. So somehow in this case, the impurity disorder is actually making the system easier to localize, easier to turn into some kind of insulator. In this case, it's not really clear the incommensurate lattice is doing much of anything to the system and changing the way that you go from a superfluid to a non-insulator. Okay, and they saw similar things in a coherence measurement. All right, so I think this is an experiment which I encourage you all to read this paper and think carefully about it. And this is an example where they saw something really quite significant happen with the impurities, where the transition from a superfluid to a non-insulator, this is lattice depth here, so the non-insulator lies out here somewhere, is shifted to lower lattice depth with the impurities present. So in this case, the disorder is making the system more susceptible to being an insulator. Okay, this is complicated. Maybe we should skip on to something else. Let me talk about 2D dirty bosons. There's been one experiment with 2D dirty bosons, and that's an experiment from Steve Rolson's group. And this is the experiment where they trap the atoms in a pancake, actually two pancakes. So they have a optical lattice here, and they trap the atoms in two sheets. They're using bosons. They start with a BEC, and it's kind of a continuum model. So they have atoms just running around in a sheet, and they apply speckle disorder to it. Okay, in this case too, there was probably an issue where the atoms were strongly trapped in that speckle classically, and what effect that had on what they observed, I'm not sure anybody knows. So the measurement they did was they allowed the atoms, they released the atoms, and they allowed the atoms in these two pancakes to expand into each other and interfere. And those atoms form an interference pattern, which you can observe here, and in this case there's actually a vortex present in one of the layers, which is why these things get kind of kinked. Okay, so then what they did was they looked at how, for example, disorder affected the visibility of this interference pattern. And so they did a bunch of measurements. They actually, in this experiment, they varied temperature. And they looked at, so for example, here is a plot of visibility. This is disorder strength. This is temperature going along this axis. So you can see as they crank the temperature up, they get poorer and poorer visibility of those interference patterns. And as they crank the disorder up, they get poorer and poorer visibility. And somewhere out in the regime of high disorder and or high temperature, they're seeing the system lose all visibility or come close to losing all visibility. So this looks like some kind of localization phenomenon. But I would say it's, in this experiment, it wasn't clear exactly what was happening.